Find the first five terms of the sequence of partial sums, round to four decimal places. We have a series of terms that are being added together. We have 1 over 2 times 3 plus 2 over 3 times 4 plus 3 over 4 times 5, and so on. S sub 1 is the first term, which is 1/6. And I went ahead and rounded these to four decimal places. That's what you're asked to do in WebAssign. S sub 2 is the sum of the first two terms. So that's 1/6 plus 2/12, which is another 1/6. That's 1/3 decimal form. S sub 3 is the sum of the first three terms. So that's 1/6 plus 1/6 plus 3/20, and so forth. And again, in WebAssign, you're asked to do that to the round to four decimal places and do that for the first five terms. So you have a sequence of sums, which is a partial sum of your entire list. The second example we did in class, we have a sign alternator. When n is 1, 1 plus 1 is 2, that's even. -1 to an even power is going to be +1. 1 factorial is defined as 1, so 1 over 1 is 1. When you move your index from 1 to 2, when n is 2, that's -1 to the 2 plus 1. -1 to an odd power is -1. 2 factorial is 2 times 1, that's 2. So our second term is -1/2. And what we're doing is we're just building a pretty good list, 5 terms specifically, so that we can slowly add them up. When n is 3, 3 plus 1 is 4, that's even. -1 to an even power is positive. So you notice that you go positive, negative, and so forth. That's why I call that a alternating sign. It's generates positive and negatives. The factorial, the way it's defined is, for example, 3 factorial. You take your number, whatever factorial it is, in this case 3, and you consecutively count down to 1, and you multiply all the numbers in the list. So 3 factorial is 3 times 2 times 1, which is 6. Anyway, we have generated, if you're careful, go from n equals 1 up to 5, and that'll generate your first 5 terms. The partial sums, you do them one at a time. So the first term is 1. The sum of the first two, 1 minus 1/2 is 1/2. The sum of the first 3, we have 1 minus 1/2, which is 1/2, plus 1/6. 1/2 plus 1/6, that's 4/6 or 2/3, and so forth. Then you would add your first 4 terms. Just feel free to use your calculator, and you keep a running total. That's what this sequence of partial sums does for us. For the infinite series, the sum from 1 to infinity of an nth term that'll be given, a sub n, the nth partial sum is the sum of each term in the series added up. If the sequence of partial sums converges to a finite value s, then the infinite series converges. The limit s is called the sum of the series. So that's the importance of knowing whether a series diverges or converges, is if it converges, then there's a sum that series will add up to. Let's investigate. First example, find the sum of the series, which we have the sum from 1 to infinity of 1 over 2 to the n by finding the limit of the sequence of partial sums. So in the examples we did before, we were used to generating 5 terms of partial sums, and we're going to do that here. So let's make out a list of the first 5 terms of this infinite series, starting with 1 over 2 to the first, plus 1 over 2 to the second, plus 1 over 2 to the third, and you do that for the fourth and fifth terms as well. Now, the sequence of partial sums, we take our first term, which is 1/2, that's s sub 1, S sub 2 is the sum of the first two terms, a half plus a fourth, 3/4. S sub 3 is the sum of the first three terms, 7/8, and so forth. Now, when you look at these terms of partial sums, it's a sequence of sums. If you can develop a pattern for these sums, notice the numerator is always one less than the denominator. And the denominator is whatever term you're on as a power of 2. 32 is 2 to the 5th, 16 is 2 to the 4th. See how those subscript values match your power of 2? So when we come over here in the pink, the denominators are all powers of 2 based on what partial sum you're trying to calculate. The numerator was always one less, so we take our denominator, 2 to the n power, subtract 1. Now, when you apply a limit and you let n get really large in this nth term of partial sums, what you find is when n gets really large, this -1 doesn't amount to much. The limit as n goes to infinity for 2n over 2n, after you kind of ignore the -1, there's really some division that goes on behind the scenes, but ultimately, when you go into infinity, you look at your largest terms. Now, since they're identical, that's going to be 1. And it turns out that's the sum of this series. Now, we're going to revisit this series in a little bit because it turns out that this is a geometric series, and those are, if you can recognize a geometric series, it's very easy to determine if they'll converge, and if they converge, what the sum of that series will be. A telescoping series, think of a pirate movie where you see the pirate pull his telescope out, he extends it. I'm really not sure if they're called telescope. I think there's some other word for it. But anyway, where you pull it out, look, and then you can punch it back in. Finding the sum of a telescoping series is going to work the same way as the problem before. We're going to generate a list of partial sums, a sequence of partial sums, and see if we can't find a pattern. If we can find a pattern, then we'll let a limit as n goes to infinity and see if we get a finite value. All right, S sub 1. Remember, we're letting n start at 1 and increase one at a time. So with n equals 1, that's 1 over 1 plus 1 over 2. Excuse me. 1 over 1 minus 1 over 2, which is 1 minus a half. I'm not sure why I wrote that. I'm going to fix it though. It should be equals. S sub 2, when you put the second term in, that's going to be 1/2 minus 1/3. So you have the first term plus the second term. S sub 3 is the sum of the first three terms. So we already know the first couple terms in this series. The third term would be 1/3 minus 1/4. Now, if you keep this up, you develop an S sub n term, which is when n equals 1 plus n equals 2 plus n equals 3 plus ... All the way at the end, we have our nth term. Notice back here in that last set of parentheses, it matches our original a sub n term. The one before that would be 1 over n minus 1 minus 1 over n. If you take away 1, reduce n by 1. When you go through your list, you'll notice that -1/2 and +1/2 will cancel. -1/3, +1/3 will cancel. The only terms that don't cancel is the first term and the last term, 1 minus 1 over n plus 1. So the reason we call it telescoping is we expand this out. After your cancellations, it collapses back down. So we have S sub n, it telescopes, it extends way out, But after all the cancellations are done, you're left with, in this case, the front and the last term. As n goes to infinity of your s sub n term, this fraction goes to 0, fixed numerator, growing denominator, so that goes to 0, leaving you with a value of 1. And it turns out that's the sum of that telescoping series. The example that we did on the last slide, and I mentioned it being easy to recognize as a geometric series. A geometric series, if you can write your infinite series in this format, where you have a leadoff term and a ratio that changes, then the sum of that infinite series will be a over 1 minus r, as long as that ratio's absolute value is less than 1. So back on that previous example that I noted on the last slide, 1 over 2 to the n, 1 to the n is still 1. So what I did was I included the 1, calling it 1/2 to the n power. You can kind of finagle these series around if you're careful. Like, notice the starting index is 1. If you reduce your index, then you increase the n term. Now, I only reduced by 1, so I only increased by 1. By property of exponents, I can now call that 1/2 to the first times 1/2 to the n. That's still n plus 1, it's just split up. Now, because, let's see, that should be a 0. Now, because I've generated this format, the series, so we're going to take the sum from 0 to infinity of 1/2 times 1/2 to the n. This half represents my a value. It's the first term of the series. If n equals 0, 1/2 to the 0 is 1, times a half is a half. So 1/2 is my first term of the series. The ratio means that it's changing by multiplying by progressive powers of 1/2. So that's the ratio of change. Well, 1/2 is less than 1, so this is a convergent geometric series. And if you take a over 1 minus r, you get a value of 1. So that sum from this geometric series is 1. Now, on the last slide, when we developed a sequence of partial sums, that pattern was 2 to the n minus 1 over 2 to the n, and it also had a limit of 1. So you can do it either way, and if you'll notice, your answers do match. Let's do one more infinite series, this time with partial fraction decomposition. This was a skill we learned back in the last unit of how to decompose a fraction into simpler terms. 2 over 4n squared minus 1, that is a difference of 2 squares. So over here in purple, I'm taking my a sub n term, factoring the denominator, 2n minus 1, 2n plus 1, creating 2 simpler fractions with each factor as the denominator. And now also notice these factors are linear, so you build a constant numerator. The numerator was always 1 power behind the denominator. Multiplying this fraction and these two by the least common denominator, that's going to leave you with the numerator of this fraction. Crisscross these two terms, that's a times 2n plus 1 plus b times 2n minus 1. Now be very careful, if we want to zero out each term, this term goes to 0 when n is negative half. This term goes to 0 when n is positive half. So that's a good choice to let n be values that zero out each variable term at a time. Makes it easier to calculate. All right, so if n is a half, 2 times a half plus 1 is 2, so 2 equals 2a. This term goes to 0. That tells us a equals 1. So that's our numerator for 2n minus 1. When n is negative half, We have 2 equals 2 times negative half plus 1 is 0. So that zeroes out the a term, even though we now know what it is. 2 times negative half minus 1 is negative 2. 2 divided by negative 2 is negative 1. So that's the value of b. Now that we know a and b, we can rewrite this a sub n term as the difference of those two simpler fractions. Now what that does is that lets us create a telescoping series S sub n, and again I'm going to use these two fractions. When n is 1, plug them in, you get 1 minus a third. When n is 2, plug into both fractions, you get 1/3 minus 1/5. When n is 3, 1/5 minus 1/7. So you create a telescoping list. This is the expansion part of it. Once you run into consecutive cancellations, count how many terms in the front still exist. Now, if there's 1 or 2 terms that don't cancel in the front, then that means there's going to be 1 or 2, respectively, terms from the back that don't cancel. Well, since we only have 1 term in the front before the consecutive cancellations occur, there's only going to be 1 term in the back. So this is our S sub n term once you telescope out, cancel, and collapse back down. The limit of that S sub n term is going to be 1. This fraction goes to 0 as n gets really large, so 1 minus 0 is 1. And that's the sum of this telescoping series.